Hey guys, thank you for checking out this video. If you want to start learning about semiconductor packaging, then you're in the right place. This is Lito Galera and welcome to my Watch, Learn and Play channel. So what is semiconductor packaging? Semiconductor devices are made in wafer form. Each wafer contains hundreds or thousands of devices or silicon chips as we also call it. Semiconductor packaging is actually a series of steps from cutting the wafer into single chips and to transform them into a molded single device that is ready for use to make an electronic system. Semiconductor packaging involves many processes, and this slide shows the basic process flow. Wafer saw is the process of cutting the wafer into individual chips, or commonly called as die. Die attach is the process of mounting or attaching the die to a lead frame. A single device or die has multiple input or output terminals. Wire bond process is a step that connects each die input or output terminals to individual pins or leads of a lead frame. Molding is a typical method of encapsulating the bonded device. Once molded, the device is protected from damage due to handling and also from environment. Marking step adds information about the device and makes the molded device visually identifiable. Plating, trim form singulation, and final tests are the final steps to complete the packaging process. I will discuss in the next slides more details of each process steps. So if you're still interested, just hang in there. Wafer saw is the process of cutting the wafer into individual chips or dies. Wafers are brittle. They break easily if not handled properly. And because each wafer contains many chips, the cost of accidentally damaging or breaking a wafer is quite expensive. In other words, wafer saw process is a delicate step and can be very costly if not done properly. Let's talk a little bit about wafer sizes. Wafer comes in different sizes. Wafer sizes that are in mass production are 4, 5, 6, 8, and 12-inch diameter wafers. 4 and 5-inch wafers are mostly for discrete devices, which are diodes and transistors. Because they are single devices, they are typically small, mostly less than 1 square millimeter in area. With their small size, a 4-inch wafer diameter can hold thousands of diodes or transistors. 6-inch wafers are common for power transistors and low pin count ICs. These are slightly bigger devices, can be up to 3 millimeter in length or width. 8-inch wafers are common for high pin count ICs, and also in some low pin count ICs and power discrete devices for better manufacturing costs. The most expensive wafer is a 12-inch diameter wafer, which is for advanced high pin count ICs. 12-inch wafers also require more advanced equipment as it is more prone to breakage. Let's continue on with the wafer saw process. To prepare the wafer for sawing process, it has to be mounted on a tape. The tape will hold the wafer or dies in place during and after the sawing process is complete. This preparation step is commonly called the wafer mount process. In this step, the tape is attached to a metal ring or a wafer ring, and the wafer is mounted onto the tape. Here is a short video of a wafer mounting process from Ultron Systems. I edited the video a little bit to add titles of sub-steps, but you can watch the unedited full video using the URL provided on this slide. Let's begin. Once the wafer is mounted on the tape, it is now ready for sewing or dicing process. The cut must be done along the saw streets, as center as possible, making sure that the active circuit of the die will not be damaged or chipped during the process. The sewing process is done using a diamond blade. These type of blades are specially made blades for cutting silicon wafers. After the sewing process, the dies are now ready for die attach. Here's a short video of paper sewing process. You can watch the full video using the URL provided on this slide. Let's watch it. Die attach is the process where the die is mounted or attached onto a lead frame or substrate. In most applications, particularly ICs, attachment is done using silver-filled adhesive epoxy. For diodes and transistors, it can be a soft solder or eutectic method. Mainly, the selection of the attach method is dependent to device application. In this video, I will focus on using lead frame and epoxy die attach method. This image shows a single unit or cell of a lead frame. Each unit has leads and the attach pad. The adhesive epoxy is dispensed onto the die attach pad, and the die is placed and pressed onto the epoxy to form epoxy fillet on the side of the die. Before we continue discussing the attach process, let's discuss a little bit more about lead frame and substrate. Lead frames are made of copper alloy. Copper is a very good electrical conductor, which is very important material property for electronics application. Likewise, copper is inexpensive. It is cheap. These characteristics of copper makes it ideal in semiconductor packaging application. Lead frames are typically designed in matrix form, which means having multiple rows and columns. This type of design maximizes number of units or cell per lead frame, or what is called lead frame density. The higher the density, the lower cost per unit, which is ideal for manufacturing. Lead frame is suitable for both discrete and IC devices, and for both low and high pin count packages. Laminate substrate is for BGA type packages. It is made of laminated layers of prepreg and copper, allowing high density interconnection for high pin count ICs and high-end advanced packaging. Like lead frame, laminate substrate is also designed in matrix form. Laminate substrate is usually more expensive and cost is dependent on the number of layers it is made of. Let's continue discussing the attach process. A full attach process involves several actions happening all at the same time. This is important to maximize productivity and thus lowering production costs. The process is done using high-tech, high-precision machines. This slide will illustrate the typical process diagram of die attach process. The lead frame loader is the input side of the machine. It is where the stack of lead frame or substrate is placed. The lead frame is picked up from the loader and fed to the work holder system. The work holder system precisely moves or indexes the lead frame from input to output side of the machine, with the timing of movement being controlled by machine software. The adhesive dispenser is located on the input side of the work holder system. Epoxy is dispensed onto the die attach pad every time the lead frame is indexed. The bond station is where the die is placed and typically is on the middle part of the work holder. Vapor handler is where the vapor is held, usually opposite the work holder. Underneath the vapor is the ejector assembly, which pushes the die up so it can be picked up by the pick and place system. The pick and place system or bond arm picks the die from the vapor and place it onto the lead frame die attach pad at the bond station. This cycle repeats continuously, with the lead frame indexing every cycle until all the good dies on the vapor are picked up. Once the lead frame is full, it is then pushed out to the output station, going into an output magazine or carrier. The magazine is unloaded once full. The process starts from left side of the machine, going to the right side of the machine. It is very important that only the known good dies, also called KGD, are picked during the attach process. Otherwise, it will be a waste of material and time processing the bad dies. Let's step back a little bit to explain about KGD, ink dye, and vapor map. Each vapor, after fabrication, undergo electrical testing, also known as vapor sort process. At vapor sort, each die is electrically tested to the device specification. Every die that fails electrical test is inked. Therefore, if you see a vapor with ink dyes, it means that those dyes are bad. A more advanced vapor sort process does not ink the vapor dye, but rather a vapor map is created. A sample of vapor map is shown on the right side of this slide. It is basically consists of ones and zeros, where 1 means good and 0 means bad. Because there's already a vapor map, inking the bad dye is not anymore necessary. Here's a short clip of the attach process in action. You can watch the full video using the URL provided on this slide. After the attach process, all materials must be put in the oven to cure the adhesive epoxy. After the attach, and once adhesive epoxy is cured, the die is now ready for wire bonding. Wire bonding is an interconnect process and is a complex process, and it gets more complex as the number of leads or input-output terminals increase. The objective is to connect each die terminal or bond pods to corresponding leads of the lead frame. The bonding cycle is repeated until all bond pads that require connections are bonded. So, for a device that has 64 input-output terminals, the bonding cycle will execute 64 times. Before we talk about bonding cycle, let's discuss the different wire types in wire bonding. Gold wire is the most popular and most commonly used for ball bonding, mainly because gold is very good conductor and soft, which is suitable for aluminum bond pad. The downside of gold wire is it is very expensive. Copper wire is an alternative material to gold, especially that it is a better conductor. Copper, however, is harder than gold, which makes it tougher to bond, and also oxidizes quickly at high temperature. But gold price started to go up significantly in early 2000, thus the conversion to copper wire was inevitable. Silver wire was also developed for low-cost ball bonding. Silver is also a good conductor, although inferior than gold and copper. It is, however, softer than copper and less prone to oxidation. Aluminum wire is as old and popular as gold wire. It is, however, used for wedge bonding. Because aluminum is cheaper, it can be used in larger diameter. Larger wire diameter can carry higher current. Thus, aluminum wire is mainly used for power semiconductor devices. Let's now discuss the structure of a wire bonded device. On the left side of this slide shows components of a bonded device, which includes the device itself, or what we call die, which sits or attached to the die attach pad. The wires connect the die to the leads. A more detailed illustration is on the right side. The bonded ball is bonded onto the bond pads, and the stitch is bonded onto the lead, and the wire loop that is formed between the bonded ball and the stitch. Let's now discuss the most important topic of wire bonding process, which is the bonding cycle. The cycle starts with capillary on idle starting position with pre-air ball hanging on its tip. The capillary will then start to descend at the controlled speed, and the pre-air ball now securely sitting on the capillary tip. The capillary will continue to descend until it touches down onto the band pad. At touchdown, a controlled bond force is applied through the capillary, which is held by the transducer. The bond force controls how the pre-air ball is pressed or mashed onto the band pad. The ultrasonic power is then applied by the transducer for a certain amount of time, where the scrubbing action of the mash ball to the band pad happens to form the banded ball. At this stage, the first band cycle is complete. After the first band, the capillary will move up to a kink height, which is the start of the wire loop formation. The capillary will then move for a reverse motion, which is to bend the wire in preparation to forming the actual wire loop. After reverse motion, the capillary will then move towards the leads, following a motion set on the loop parameters of the machine. The capillary touches down onto the leads to form the stitch or second bond. The capillary will then move up to break the wire and form a tail on the capillary tip. A high voltage spark will then melt the tail to form a new pre-air ball for the next bond cycle. Let's now watch the actual bonding in slow motion to understand more of the bonding cycle I described in the previous slide. Just like the previous clips, you can watch the full video uh, using the URL provided on this slide. Let's watch. For high volume mass production, it is always desirable to do high speed bonding for maximum productivity to lower manufacturing costs. Let's watch high speed bonding in action in this clip. As usual, you can watch the full video using the URL provided. We have completed three main processes, which are paper saw, die attach, and wire bonding. If you like the video so far, please don't forget to click the like and subscribe buttons. An exposed bare die is already prone to damage due to handling. An exposed wire bonded die is much more prone to handling damage due to wire being very soft and protruding higher than the die. Also, any movement or flexing of the lead frame will break the bonded wire. In many applications, semiconductor devices are put into extreme environmental conditions. These include very hot temperature, freezing weather, and high humidity. All of these can cause damage to the device. In this regard, the semiconductor device has to be encapsulated or molded after wire bonding. At least the die side or top side needs to be molded. Depending on the package type, the bottom side may be molded as well. The molding material is called epoxy molding compound or EMC and typically in pellet form. Transfer molding is a typical process for molding semiconductor devices. In a transfer molding process, the lead frame is placed on a heated mold cavity and clamped very tightly. The EMC is placed and melted through the transfer pot. The molten EMC flows through the runners and to the cavities, molding individual units of the lead frame. Multiple lead frames are processed in a single mold shot. We are now at the home stretch of the packaging process. After molding, the device is technically unidentifiable. There's really no indication of what device is inside the package. Thus, after molding, the package has to be marked. In the marking process, several important information are printed or engraved on the package. The information include company logo, device code, manufacturing date code, manufacturing location code, and pin 1 orientation. The size and amount of information is dependent or limited to the size of the package. A sample image on the right is an IC device made by Analog Devices. After marking process, the next step is to have the copper lead frame thin plated. Thin plating the copper leads provides resistance to corrosion and also good solderability that is suitable for electronics application. And finally, after thin plating, the package are now ready to be liberated to be an individual devices. Trim, form, and singulation, or TFS, is a series of steps that are done sequentially within the same machine. Trim step removes the tie bars to separate the leads. Form step is the forming of the leads, typically galving form. And finally, singulation step separates and singulates the device from the lead frame. That completes the packaging process. After packaging, the devices are all electrically tested to their specifications. Obviously, only the aesthetically good and electrically good devices are sold in the market. I'll be uploading more videos related to wafer saw, die attach, and wire bond with more process details. Don't forget to like, subscribe, and share my channel and this video. Thank you for watching. Hey guys, welcome to another learning session. And this time I will talk about vapor soap process, which is technically the first process step in semiconductor packaging. This is Lito Galera and welcome to my Watch, Learn and Play channel. Vapor soap process has two main steps. First is the mounting of the vapor onto the dicing tape. We call this step as vapor mount process. The vapor mount process is simple and direct. However, it can cause significant problems if not done properly. After mounting, the vapor is ready for dicing process. I will discuss the details of these two processes in the next slides. Let's see the vapor mount process in action by watching this video from Ultron Systems. You can watch the full video using the URL provided on this slide.
The Model UH114 series wafer frame film mounters are able to consistently and uniformly mount a wafer to a film frame in several easy steps. First, load the film frame and wafer onto the machine. Then, turn on the vacuum switch to hold them into position. Pull the film evenly over the wafer and film frame and attach it to the front tension bar. Next, pull the laminate roller assembly completely forward, then return it to its home position. Close the lid and rotate the circular cutter 360 degrees to cut the film along the film frame. Slide the end cutter, open the lid, and remove the excess unmounted film. Finally, turn off the vacuum switch, and the process is complete.
I highlighted three key parts in the video. First is making sure that the vapor stage or chuck is clean and free of debris before putting on the vapor. You notice that the vapor is spacing down when placed onto the chuck. If the chuck surface is dirty or contaminated, that dirt may transfer to the vapor and contaminate some good devices. Worst case, if there's a debris on the chuck, it will make the vapor not sitting flat and that will lead to vapor breakage when the vacuum is turned on or when the tape is rolled onto the vapor. These are small things but can cause serious problems. The second thing that I highlighted is the loading orientation of the vapor. Notice that the vapor has a flat side. This flat side is a guide for proper and consistent vapor orientation when mounting and cutting the vapor. This same orientation will also be used as reference to subsequent process, which is the die attach process. If vapor is mounted and cut with the wrong orientation, it is likely the vapor will be unusable, either at dicing process because of misaligned cut or at die attach due to misoriented die. Some dicing machines may be able to detect this misorientation, but if your process don't have that advanced equipment, then you're likely to have a major problem. That's why it is better to make sure that vapor is mounted with correct orientation. Lastly, the mounting quality, which is the adhesion of the vapor to tape, must be bubble-free. An air bubble between tape and vapor means there's no adhesion between the two materials. Without proper adhesion, the die will fly off from the tape during dicing process and this can cause blade breakage and may also damage the vapor. Needless to say, air bubble on tape must be checked carefully after vapor mounting and also before dicing process. There are two main types of mounting tapes. One is a typical blue tape and the other is the UV tape. Interestingly, the reasoning for choice of mounting tape is not mainly affected by dicing process, but rather by the die attach process. I will discuss this in detail in the die attach process video that I will release soon. But for now, I will just talk about tapes in the next slides. Let's talk about the difference between the typical blue tape and the UV tape. Blue tape can be considered as all-purpose tape. It has a good adhesion suitable for dicing process, and also for die attach process for most devices or die sizes except for large thin die. It is also cheaper compared to UV tape. UV tape has a much higher adhesion strength, which is very good for dicing process. But once exposed to UV light, the adhesion strength is almost nil, which is ideal for die attach process, particularly for large thin die. UV tape is mainly used for high-end ICs in advanced packaging. This slide shows further comparison between blue tape and UV tape. Values shown here are typical and were extracted from a material datasheet. I highlighted in the blue box the very significant difference in values of adhesion to silicon wafer between the blue tape and UV tape. Tape adhesion is critical in the dicing process. Without enough adhesion, part of wafer or die may come up during dicing process, which will cause damage to both the wafer and blade. Tape adhesion also affects the next process step, which is the die attach process, mainly because of the die size. The illustrations on this slide explain the different adhesion level between different tapes and different die sizes. At wafer form, the contact area of wafer to the tape is equal to the surface area of the wafer, which is the maximum adhesion possible. However, the adhesion is reduced as the dicing process progresses. Once dicing is complete, the adhesion is already reduced to the area of the die. For small die on the blue tape, the adhesion is low, which is ideal for die attach process. For a large die on the blue tape, the adhesion is higher due to larger contact area compared to a small die. And for the same die size, the die mounted on UV tape is sticking more than the one mounted on blue tape. Let's now talk about the actual dicing process. And let's start by watching this short video. As usual, you can watch the original full video using the URL provided on this slide. That short video showed the three main steps of dicing process. First is the wafer alignment, followed by dicing process, and finally quality check. I will discuss these key steps in the next slides. Why wafer alignment is critical? Every wafer is mounted differently in terms of angular position. A wafer may be rotated a bit more to the right, or a bit more to the left, or just right to look straight. So why wafer alignment is important? For illustration purposes, let's capture a small portion of the wafer and assume it is perfectly straight or aligned. The soy street is the space between two dies. To achieve a good cut, the blade cutting line must be in the middle of the soy street. Take note that the blade linear position or alignment is fixed. With this, the wafer, specifically the soy street, must be straight and parallel to the blade. Otherwise, the cut will be misaligned and the cut wafer will be unusable or scrap. There are two ways to align the wafer. One is manual alignment, which is done by aligning the soy streets on the left side and right side of the wafer. On actual machine, the camera will zoom in and focus on the left side of the wafer, and the screen will show the crosshair position relative to the soy street. The operator will move or rotate the wafer to line up the soy street to the crosshair, after which the same is done on the right side of the wafer. This is done back and forth multiple times until the crosshair is aligned on both sides of the wafer. Manual alignment is usually used when cutting a blank silicon wafer, or a wafer with no unique pattern, and in some cases when cutting a small piece of wafer, that is, salvaging some pieces from a broken wafer. The other and better method of aligning the wafers by auto alignment. Auto alignment uses PRS, or pattern recognition system. PRS is an old vision technology but very powerful, and is common capability in many semiconductor equipments, old and new, particularly saw, die attach, and wire bond machines. In an auto alignment method, the user will select and teach a unique pattern that the machine will use as a template for wafer alignment. The PRS system is able to detect position and rotation of the taught pattern and translate that to the position and rotation of the wafer. With the PRS information, the wafer rotation, which is the wafer theta alignment, is adjusted automatically until the wafer is aligned or straight. This image shows the parameters in play in the dicing process. Of course, there is the tape and wafer. The blade is mounted on the spindle assembly. Feed rate is a speed of feeding the wafer onto the blade. The DI water is to cool down the blade, and also it helps to immediately wash off the silicon dust. Wafer wash is another step after the cutting process. This can be an integrated step built within the saw machine for a full automatic system, or a separate machine just for washing purposes. Note that the silicon dust may deposit and contaminate the device band pads if not washed immediately and properly. One of the first things that comes to mind when talking about sawing or dicing process is definitely the blade. Like, you can't saw if there's no blade. So it's now time to talk about blades. Blade exposure and thickness are key properties when selecting a blade. Blade thickness affects the kerf width, which is critical to dicing quality. And obviously, a thinner blade is needed for narrow saw street. And blade exposure is affected by required cutting depth and wafer thickness. In general, blade exposure, kerf width, and cut depth are related to blade thickness and can be calculated or predicted using these formulas. Recommended blade exposure is less than 20 times blade thickness, or maximum 30 times blade thickness. Of course, theoretically, more blade exposure means longer blade life. However, a large blade exposure means blade can be wavy or wobbly during cutting process, which is high risk for blade breakage. Kerf width is about 10% wider than blade thickness, or cut depth should be less than 10 times blade thickness. If deeper cut is necessary, it should be no more than 15 times blade thickness. The blade for dicing process is a diamond blade, but note that the diamond is not real. Diamond refers to the diamond grits, which are synthetic material. The actual blade is mounted on a hub with a narrow edge exposed around the hub. The key properties of diamond grits are grit size, concentration, and bond type. All these properties affect dicing quality and blade wear. Grit size is about how small or large the grit is. Concentration is the density or the approximate number of grits on the blade. This is either high or low concentration. While bond type is how the grits are held together to form the blade, which can be a soft bond or a hard bond. Here are simple charts showing the relationships of grit properties versus dicing quality or chipping, and also blade wear. The left chart is for grit size, which shows that smaller grit size will likely reduce chipping. However, the blade wear is faster. With larger grit size, blade wear is reduced, but likely there is a tendency to have more chipping. On the middle chart, high concentration tends to reduce the top or front side chipping, and also improves blade wear. but it somewhat increases the chance of backside chipping. The right chart shows the relationship for bond type. The soft band is good in reducing chipping issue, but has the opposite effect in terms of blade wear. A new blade is immediately ready for use to cut a wafer. However, while it is good to use, it is actually not at optimum condition for best cutting quality. The reason is the exposure of diamond grits on a new blade is shallow and may be uneven. Blade dressing is the process of uniformly exposing the diamond grits. This is done using a dressing board or plate, cutting at a very slow speed for a certain number of cuts. Equipment or blade supplier usually have recommended recipe for blade dressing. The user can optimize the recipe for a specific application. Blade dressing also helps on the truing of the blade, which is the correction of blade center line relative to the spindle. In summary, to select a dicing blade, you will need both wafer and tape information. For wafer, you need to know soil street width and your target curve width, and also wafer thickness, passivation material, and soil street material or metallization. For tape, you need to know the tape thickness. Once you have this information, you can then select your blade based on blade thickness, exposure, and grit properties. The image on the right gives you some information about blade nomenclature from Disco Corporation. We have discussed a lot about mounting tape and dicing blade. So it is now time to discuss the remaining parameters of dicing process, which are the spindle rotation speed and cutting feed rate. The spindle rotates at a very high speed, approximately 30,000 rpm to 45,000 rpm. The wafer is fed to the spinning blade at a speed or feed rate of approximately 10 to 80 millimeters per second. Let's look at these simple charts for spindle RPM and saw feed rate, and how they affect sawing quality and blade wear. For spindle RPM, a higher RPM tends to reduce chipping and also improves blade wear. However, if the spindle RPM goes too high, the positive effects are reversed. That means chipping may increase and blade wears faster. For feed rate, a slow feed rate tends to reduce chipping and blade wear, which are good. However, because it is slow, productivity or throughput is also low, which is not desirable for high volume manufacturing. We have covered wafer alignment and dicing process. It is now time to discuss quality check after dicing process. Let's look at this image of a portion of a sewn wafer to understand dicing quality. The large dark brown color is the die active area. The soil street is the area inside the narrow lines from the edge of the die. The curve is the cut line and measured as curve width. On the top left is the illustration of a good cut. A good quality cut has the curve in the middle of soil street with no chipping that extends to the die boundary or active area. An example of a bad quality cut, which is a reject, is shown on the bottom left side of this slide. That is an excessive chipping on the die top side that extended to the boundary of the die. Another example of bad cut is a misaligned cut. That is, the cut line or curve is along the die boundary or die active area. Chipping does not only happen on die top side. It is not uncommon that it also happens on die back side. Although die back side has usually no active circuit, it is typically not acceptable to have backside chipping that's more than 25% of die thickness. To summarize, we have covered in this video the different mounting tapes, which are blue tape and UV tape. We also talk about blade parameters such as grit size, concentration, and bond type, and also blade dressing. We also covered the importance of paper alignment and comparison between a manual and auto alignment method. And lastly, we talk about dicing quality, which is about top and backside chipping and cut line accuracy. Coming up next are learning videos of die attach and wire bond processes. Thank you for watching. Hey guys, thank you for checking out this video. This time I will give you an overview of die attach process, which is one of key processes in semiconductor packaging. I'm Lito Galera, and let's start learning. You just saw the die attach process in action. The process involves multiple machine subassemblies that are in motion wherein timing of each movement is very important for the process to work properly. Let me discuss the die attach process in more detail. The work holder does the handling of lead frames or substrate from input to output stage. The input loader takes stacks of lead frame or substrate and feeds them to the indexer. The indexer moves the lead frame or substrates from input to output and sync with the dispenser and pick and place assembly. The epoxy dispenser is mounted along and over the indexer. The epoxy is dispensed on every program position of the die attach pad or DAP. For soft solder die attach, the epoxy dispenser is replaced by a solder wire feed station. While for eutectic die attach process, there is no epoxy dispenser or solder wire station. The output handler collects the completed lead frame or substrate to a carrier called magazine. The wafer handler, as the name implies, handles the sewn wafer that is mounted on a tape. The tape is expanded once loaded onto the wafer handler to have larger spacing between dies. Without tape expansion, the die, during pickup, will hit or bump the adjacent dies, and that will cause die damage or chipping. The pick-and-place system includes a bond arm and ejector subassemblies. The bond arm picks up the die from the wafer and mounts it onto the lead frame or substrate. Depending on manufacturer, some machines have straight or linear bond arm, and while others have swivel arm. The ejector assembly is mounted in the middle and below the wafer handler. A special ejector needle made of steel or tungsten carbide is used to eject or push up the die from the mounting tape. In some cases, particularly for thin die application, plastic needles are used. It is important that only the good dies are processed and the bad dies are left on the tape. The common method for screening the good and the bad dies is using a pattern recognition system, or PRS. The PRS, if programmed properly, will recognize the unique pattern of a good die and also can recognize the ink dot. As each die is scanned, the machine will skip picking up the ink dies and pick up only the good dies. The die attach process has certain specifications that are important and critical to device performance. Epoxy coverage is expected to be 100% under the die, and with visible epoxy fillet of at least 90% on each side of the die. If these requirements are not met, the device can be rejected due to quality concern. It is quite common to hear BLT when discussing the attach process. BLT stands for bond line thickness. This is the thickness of adhesive epoxy under the die. Typical requirement is at least 25 microns before epoxy curing. To meet epoxy coverage and BLT requirements, it is important to dispense the correct amount and shape of epoxy, and also to control bond height. Correct epoxy volume can be achieved by using dispensing nozzles that are designed for specific die sizes, and by optimizing the dispensing process parameters. Another die attach requirement is a die placement and die orientation. The die placement and orientation is driven by wire bonding layout and is specified in the build diagram. Typically, the die is placed on the center of the die attach pad, but in some cases it can be on the left or right side of the pad and can also be rotated at a certain angle to accommodate wire bonding requirements. That completes the die attach process overview in this video. I will discuss in the next slide some details about process setup. If you want to continue learning about the die attach process, then just stay on. As I mentioned earlier, it is important to use the right dispensing nozzle to achieve proper epoxy coverage. Because die comes in different sizes, nozzles of different sizes and designs must also be available. This slide shows the mix and match of different die sizes and nozzle design. Note that some machines have epoxy writing dispensing capability. Instead of using dispensing nozzles, it uses a single needle to dispense epoxy. The dispensing needle is mounted on a programmable motorized XY assembly that writes according to the program dispensing pattern. Let's now talk about die ejector setup. Again, die comes in different sizes. A small die requires a single needle, but a larger die must use 2 or more needles and must be configured according to die shape. Ejector setup is critical to make sure that the die is picked up properly without any damage and misrotation. A damaged die, like chipped or cracked, must be rejected as this poses a significant reliability risk. Ejector needle pushes the die up from the mounting tape at a height of approximately 1 to 1.5 times die thickness. If the die is not clear at the proper height during pickup, it is likely to hit the adjacent die once the bond arm moves to the bond position. Another thing to consider is the needle tip radius. A piercing needle has a small tip radius. It pierces through the tape and may cause microcrack on die backside during pickup, as the pickup tool is pressing on the die and against the needle. This is especially true for large thin die. For wafers that are mounted using standard tacky tape, it is common to use piercing needles, but whenever possible, it is recommended to use needle with larger tip radius. Thin wafers are typically mounted on UV tape which has zero adhesion once exposed before the attach process. This allows use of non-piercing needles for UV tape mounted wafers. Just to recap the attach process specifications. Epoxy coverage must be 100% with visible epoxy of more than 90% on each side of the die. Epoxy fillet height must be controlled at less than 75% of die thickness to avoid epoxy contamination on die surface. Epoxy on die manifestation is considered a reject. Epoxy voids under the die must be 0. Voids can lead to thermomechanical stress that can damage the die. Bond line thickness needs to be at least 25 microns with wet epoxy. But note that too high BLT might cause unnecessary die rotation issue. Die shear strength is done after epoxy cure, which is a test of die adhesion to epoxy, and also the epoxy adhesion to lead frame or substrate. A good die shear result will have sheared die as break mode. You should refer to mill standard specs for minimum shear force requirement. Feel free to drop a comment, question, or email. To support this channel, please don't forget to like, subscribe, and share this video. Thank you for watching. Hey guys, welcome to another learning session from Watch, Learn, and Play channel. This time I will discuss about wire bonding process using gold wire. Gold wire bonding is one of the main interconnect process in semiconductor packaging. It is widely used because it is a proven and stable process technology, and it is really a high throughput process that is very appropriate in a high volume manufacturing environment. Wire bonding is a complex process, and definitely there are lots of things to learn and can be overwhelming. So I will split the learning video into several parts so it won't be too long and boring and also not overwhelming. Okay guys, this is Lito Galera and let's start learning. Interconnect process is a process or method of connecting the die input and output terminals, or what is commonly called bond pads, to the terminals of the package. Wire bonding is a common interconnect method for lead frame based packages and also for BGA type packages. Another interconnect method is flip chip, which is mainly for BGA packages. There are four different types of bonding wires: gold, copper, silver, and aluminum wire. Gold wire is the most popular because of its very good electrical conductivity and malleability. However, gold is very expensive. For this reason, an alternative low-cost option is necessary. In early 2000, gold price skyrocketed, which expedited conversion to copper wire for many companies. Copper is a better electrical conductor than gold. However, it is harder and less malleable. Thus, it is more difficult to bond, and it is also prone to oxidation, which can be a reliability risk for a semiconductor device. With these limitations, there are some risks when converting from gold to copper wire. Therefore, not all devices can be converted. In most cases, use of copper wire is driven by cost rather than quality or reliability. Silver wire is another option for low-cost bonding. Electrical conductivity is not as great as copper or gold, but it is good enough. Bonding wires are not pure metal. The wires are alloyed to meet properties required for specific applications, including bondability, wire strength, and electrical conductivity. Gold, copper, and silver wires are used for ball bonding. Another popular bonding wire is aluminum. Its electrical conductivity is not as good as gold or copper, but it is a softer material and matches well with aluminum bond pad. The wire bonding method for aluminum wire is wedge bonding, and it allows use of larger wire diameter of up to 20 mils. Large wire diameter means it can carry higher electrical current, therefore it is widely used for power transistors. For this learning video, our focus shall be on ball bonding using gold wire. Let's watch again this short video of wire bonding process from TPT. You can watch the full video using the URL provided on this slide, or visit their YouTube channel TPT-Wirebonder. I annotated the video a little bit to highlight three main steps of wire bonding, which are first bond, loop formation, and second bond. Let's watch. Before we talk about the bonding process, let's discuss the bonding machine or wire bonder. A wire bonder is a complex, high-tech, state-of-the-art machine that has a very precise vision and three-axis motion system. The bonder is able to see and recognize tiny die features or patterns. These patterns are used by the machine to identify precise device location and also accurately target bonding area or position. Unique die features and patterns also serve as device identity and is recognizable by the machine. This machine capability is generally called Pattern Recognition System, or PRS. A bonding machine has many sub-assemblies, which includes material handling, optic system, bonding system, and of course a computer that controls the whole system. The diagram on this slide is a KNS automatic wire bonder. KNS stands for Kulik and Sopa, which is the company that makes the machine. I highlighted four sub-assemblies that mainly control the bonding process. The XY table carries the bond head and the optic system and precisely moves in XY direction. Bond head controls the said movement of the bonding process, and it includes the transducer that performs actual bonding process by applying force and ultrasonic power. Optic system is the precise eye of the machine that provides information to the pattern recognition system. Also, both XY table and bond head controls the X, Y, and Z movement to form the wire loop during bonding. Wire feed system controls wire movement and feeding to the bond head. Wire tension in the wire feed system is controlled through pneumatic controls and gauges. It's always good to see a video of actual bonding process. It looks simple but yet very complex due to the required precision of each step. So I created this simple animation so we can discuss the bonding cycle in more details. Note that the device is sitting on a heated surface, or what is called the heater block. Ball bonding uses heat and ultrasonic energy, thus it is a thermosonic bonding process. Also, the bonding tool is called capillary. The bonding cycle starts with pre-air ball hanging on the capillary tip. I added the two images for better visualization of the capillary, pre-air ball, and EFO1. The capillary then starts to descend at a controlled speed towards the bond pad, with pre-air ball sitting on capillary tip. Bond force is applied at touchdown, pressing the pre-air ball onto the bond pad, and ultrasonic power is applied subsequently, which completes the first bond cycle. The capillary then moves up to kink height, which is the beginning of wire loop formation. The capillary then moves forward for a reverse motion, feeding more wire for the loop formation. Capillary then moves towards the lead for the second bond cycle. After the second bond, the capillary moves up to break the wire and form another pre-air ball for the next wire. Let's see it one more time in continuous cycle. The bonded wire has three main parts. The bonded ball, which is the first bond, the wire loop, and the second bond are also called stitch that looks like a fishtail. I added sample images of bonded ball and stitch for better illustration. I will discuss each part in the next slides. First bond is the bonding of pre-air ball to the bond pad. A bond pad is a small area of thin layer of aluminum. First bond requires a small amount of force to press the pre-air ball onto the bond pad, followed by ultrasonic power to form the bond between two materials. The bond is a very thin gold aluminum intermetallic layer, and the strength of the bond depends on the amount of intermetallic formed. The bond intermetallic is formed within the contact area between the bonded or mash ball and bond pad. The larger the mash ball, the larger the contact area, and the higher percentage of intermetallic formed. More intermetallic means higher bond strength, which is ideal in the bonding process. Let's examine the bonded ball after the first bond is complete. The bonded ball or mash ball diameter is the diameter when viewed from the top view. This diameter typically should be in the range of 2 times to 4 times of wire diameter, or nominal 3 times wire diameter. For example, if you are using a 1 mil wire diameter, the target nominal diameter is 3 mils. Just to note, 1 mil is equivalent to 25 microns. Therefore, 3 mils is equivalent to 75 microns. On the mash ball diameter limit, while 4 times wire diameter may seem acceptable, it is possible that it is bigger than the bond pad opening or BPO. The mash ball diameter must be within the BPO, otherwise there is a risk of bond shorting to adjacent wire. On the low side of the limit, while 2 times wire diameter will be very likely be inside the bond pad, it is likely will result to a lower bond strength because the contact area will be smaller. Because of the inherent shape of the bonded ball, the contact area is always smaller than the mash ball diameter. Also, the bonded ball height should be around 0.6 to 0.8 times of wire diameter. The wire loop is important to clear the wire from touching any surface of the die, particularly the die edge while it forms the connection towards the lead. The wire loop must not be tight or too low to avoid unnecessary stress on the wire and prevent it from breaking. Likewise, the wire loop must not be too high, otherwise it will be exposed on top of the package. On your screen are different loop profiles according to different package size or thickness. The first illustration on the top left is an example of SOP package. SOP stands for Small Outline Package. It is a thick package, thus can allow a higher loop profile and still have enough clearance from top of the package. The second illustration is an example of QFN type package, which is a flat package. It is a thin package compared to SOP, but depending on package thickness can still allow a normal but slightly lower loop profile. A thinner flat package, as shown in illustration number 3, requires a much lower loop height and a thinner die to fit inside the package. Illustration number 4 is similar to number 3, except that the die is thicker. Notice how closer the wire to the die edge, which is almost shorting, and it's not acceptable to be considered a good product. Illustration number 5 is similar to number 4, which has a thicker die. But this time, the wire loop height is a bit higher. But notice how close the wire is to the top of the package. This is also not acceptable to be considered a good product. Finally, illustration number 6 fixes the issues of number 4 and number 5. While still using a thicker die, the wire loop profile is different. The top of the loop has a square shape, which allows lower loop height, and at the same time, by controlling the flat length of the loop, allows more clearance between the wire and the die edge. This type of loop profile is widely used in thin packages, specifically 1 mm thick or less. The second bond is the bonding of the wire onto the lead, which completes the bonding sequence. Similar to first bond, bond force is applied to press the wire onto the lead, and using ultrasonic power to form the bond. Because the second bond is on the lead, which is a much harder material compared to aluminum bond pad, it allows a much higher bond force and ultrasonic power to make the proper bond. The bond strength is relative to contact area of the wire to the lead, which is limited by the wire diameter, capillary tip size and shape, and bond pores. Let's examine the details of the completed second bond. One side of the capillary is pressed onto the wire by the application of bond pores. This forms the fishtail of the second bond as shown on the image. The lead surface will also have the capillary tip impression, showing that sufficient bond pores was applied during bonding. Notice how the shape and size of capillary tip affect the formation of second bond fishtail. Also note that second bond is also called stitch. That concludes part 1 of wire bonding learning video. The part 2 video will be out soon and I will discuss the topics shown on your screen. To support my channel, please do not forget to subscribe, like, and share. Thank you for watching. Hey guys, welcome to part 2 of wire bonding learning video. I will discuss in this video about bonding pad, capillary design, and bond quality. If you have not watched part 1 video yet, I recommend to do so as well. This is Lito Galera and let's start learning. This slide shows bond pad information for diodes and transistors. The top left photo is a die image of a diode. Diodes only have two terminals. The die back side is a negative terminal or the cathode, while the top side is a bond pad and is also the anode terminal. The bond pad size for this device is 85 by 85 microns and is composed of 100% aluminum metal. The top right image is a MOSFET die which has two bond pads, which are the gate and source. Bond pad metallization is aluminum with 1% silicon and dimensions are over 100 microns. The two bottom images are bipolar junction transistors or BJT. The top side has two bond pads which are the base and emitter. Similar to MOSFET, bond pads are approximately 100 microns or larger and composed of aluminum with 1% silicon and is 2 micron thick. Integrated circuit or IC is composed of hundreds or thousands of transistors and has many more input and output terminals. Each terminal corresponds to a bond pad. The more complex the IC, the more bond pads it has. ICs have similar bond pad compositions to diodes and transistors. But aside from bond pad metallization, there are two dimensions that should be known for ICs: the bond pad opening or BPO and the bond pad pitch or BPP. These two dimensions are critical for determining capillary design. The illustration on the right is an example of IC vertical structure or layers. Notice that the top metallization is covered by a passivation layer except the bond pad opening. Overall, bond pad compositions or metallization is 100% aluminum, with some devices having 1% silicon impurity or even an additional 0.5% copper impurity. Note that these different metallization require different bonding parameters for optimum bonding integrity. Bond pads must also be clean. Must have zero contamination on the surface for bonding to be successful with good integrity. Things to watch out are silicon dust from sewing process, and also occasionally some dies may have passivation layer overextending to the bond pad surface. Other contaminations are organic and ionic contamination. These types of contamination are not visible, therefore is very hard to detect. However, these contaminations can be avoided through proper material handling and storage. And also watch out for oxidized pad, particularly bond pads with copper impurity. One thing that's very common on bond pads is the probe mark. Wafers are typically tested or die sorted, and this is done through probing of each bond pad. Tested or sorted wafers will have a probe mark, and there must be just a single probe mark on each pad. Multiple probe marks means the wafer was retested. Multiple probe marks is not good for bonding as it disturbs bond pad surface and likely will also remove some Aluminum metallization. Probe marks must be light, not deep, and should not expose the underlying oxide layer. Let's now talk about the bonding tool or capillary. Choosing the right capillary is very important to set up a stable and reliable wire bonding process. Capillary selection starts with defining correct design or dimension. The illustration on the left is the capillary tip. Critical dimensions of capillary tip that affects first bond are chamfer diameter CD and chamfer angle CA. The illustration in the middle is the first bond, the mash ball pressed by capillary tip. For a good first bond, the mash ball diameter MBD must be within bond pad opening or BPO. A larger MBD will result to a larger contact to the bond pad and likely more intermetallic formation, thus a better bonding strength. But need to make sure that the mash ball is within the BPO. On the right side are sample photos of the gold aluminum intermetallic formation. An intermetallic of more than 60% of the bonded ball contact area is considered a good bond. This slide shows how dimensions CA and CD control the mash ball diameter. On the left side is a capillary tip with CA of 70 degrees. This tip will result to a cone or triangular shaped mash ball. On the right side is a capillary tip with CA of 120 degrees. With larger CA, the mash ball will be flatter and bigger in diameter, resulting to more contact area to the bond pad. CD also affects the mash ball diameter and more importantly the contact area where capillary is pressing on the mash ball. A larger CD will result to a bigger mash ball and larger contact to the bond pad, and likely a stronger bond. So what are the correct CA and CD dimensions? The answer to this goes back to understanding your bond pad pitch and bond pad opening. BPP will always be larger than BPO, simply because band pads cannot overlap. A large BPO and BPP will allow a larger CA and CD. A large BPO with smaller BPP may still use the same CA, but CD may be the same or a bit smaller, just to guard bond on bond shorting. For small BPO and BPP, which are called fine pitch devices, a smaller CA and CD is recommended. Since bonding starts with the pre-air ball, how do we know the correct pre-air ball size to achieve the desired mash ball size? We know that the volume of pre-air ball is equal to the volume of mash ball. Mathematically, we can calculate the pre-air ball diameter using the dimensions of capillary, target size of mash ball, and wire diameter. H is the hole size of capillary, along with CA and CD. MBD and MBH are the target size of the mash ball, and WD is the wire diameter to use. The derived formula to calculate the volume of mash ball is equal to the volume of pre-air ball. Most machines allow the users to input the desired pre-air ball size. The calculated pre-air ball diameter would be a good starting point for this purpose. And then you can fine-tune the bonding parameters to achieve the desired mash ball information. We have discussed how capillary design affects the mash ball, which technically is the first bond. Equally important is the proper bonding of the second bond, or what we also call a stitch. A good stitch bond is shown on the image on the left. The stitch has a shape of a fishtail with thickness shaped by the capillary face angle, FA. The next illustration is the capillary tip. Dimension T is capillary tip size. The stitch length SL can be estimated using capillary dimensions T and CD. SL is half the difference between T and CD. Other capillary dimensions that affects stitch shape are face angle FA and outer radius OR, as shown on the illustrations on the right side. The illustrations are examples only. If you have access to a 2D CAD software, you can draw a capillary tip with target dimensions and then project the shape of the stitch and mesh ball. This will give you a better visual of what mesh ball and stitch shapes will be. Another thing that should be considered when selecting or defining capillary design is the target loop height. Fine pitch devices have small BPP and will have tight space between wires. It is important that capillary will have enough space to not touch or disturb adjacent wires. In this regard, bottleneck type capillary is required. The illustrations show the relationships between BPP, loop height, and bottleneck height. This slide shows more detailed information about capillary. Capillaries have different material types and finishes, and also different lengths. Knowing capillary information based on part number is something good to have. The information on this slide is from Small Precision Tools or SPT. You can check their website for more capillary information. Just like any other tool, there is a limit on how long you can use a single capillary, or what's called capillary life. It is common to hear the capillary is worn out when there is a bonding issue. But in reality, capillaries are made of ceramic, which is a very strong material, and definitely do not wear out by pressing a soft gold wire. What actually happens is that there is a gold buildup on capillary tip, and this affects bond quality. In general, capillary lasts for a million bonds. Note that one wire is equivalent to two bonds because there is a first bond and second bond. Capillary is mounted on the transducer. And when replacing capillary, there are some things that we should take note and do to make sure that transducer and capillary will work as intended. Transducer screw or clamp screw also have its own tool life or limit. A worn-out screw may affect transducer efficiency, so it must be replaced when it reaches life limit. The life limit can be from the equipment vendor or from a study done by the process owner. Just to caution, clamp screw may look like just a regular screw, but its quality is critical. Do not use a cheap screw just to have a cost reduction project. Follow supplier recommendation if there's any, or buy from a reputable company that will provide you consistent material quality. Clamp screw must also be tightened at certain torque specified by supplier. Over or under tightening the screw will result to inconsistent performance of transducer and obviously inconsistent bonding results. Wire bonding is a complex process and involves many parts and parameters that are synchronized and interact at every bond cycle. Everything must be set right for the process to work. It does not need to be perfect, but definitely everything must be within specs. P-parts design and quality is critical to a consistent and stable bonding process. P-parts hold and keep the lead frame or substrate from moving during bonding process. Even a minor movement or bouncing of leads or die-attach pad will lead to a bonding issue, usually a non-stick bond. And for most devices, this is an automatic reject or yield loss. And yield loss translates to a higher manufacturing cost. Correct bond program is also critical. Pattern recognition system or PRS must be taught properly to make sure that machine will find the correct eye points at all times. This is followed by accurately teaching bond location. That is, camera crosshair is properly centered on the bond pad. Likewise, crosshair must also be centered to capillary impression, or what is called capillary offset. These things ensure proper bond placements. Preparation of devices for bonding is important. As we say, garbage in, garbage out. The devices have gone through many process steps. Bond pods and leads may have been contaminated along the way, either from handling exposure to environment and epoxy outgassing from curing die-attach epoxy. Visible contamination can be detected and screened out through inspection. The bigger enemy is contamination that we cannot see, such as organic contamination. A common method to address this is through plasma cleaning. This cleaning process is performed in a vacuum chamber utilizing oxygen and/or argon gas. Machine variability have significant impact on achieving a stable bonding process. Variability can happen within the same machine, which means inconsistent machine performance. Variability can be between machines of different make. For example, performance of a KNS bonder is different to ASM bonder. Or variation can be between machines of same make and model. For example, KNS bonders of same model have different performance. Likewise, ASM bonders of same model may have same variability. Let's now talk about bond visual quality. Because the bonds or wires are really small, to see the bond quality, the device must be inspected under microscope, usually at 10x to 40x magnification. To see details similar to images on this slide, high magnification microscope is required with magnification of at least 50x to 100x, or even higher depending on the size of the bond. The first image is an example of non-stick on pad, or NSOP defect. This is one of the most common bonding problem. On this defect, there is an impression of free air ball impact onto the bond pad, but the first bond did not stick. Usually the mash ball will be present on the lead. If there's no impression on the bond pad, it could likely be the bond pad is passivated or the bond was off target. The second defect is lifted ball. This has similarity on NSOP, except that in this case, the first bond was initially successful, allowing the full bond cycle to complete, including second bond. However, after the bond cycle, the bond lifted up. This is a manifestation of a weak first bond. Several factors may contribute to NSOP and lifted ball problems, such as bond parameters not optimized, worn out capillary, transducer clamp screw, or transducer not being calibrated properly. It is also possible that lead frame or substrate did not sit properly on the pivots, causing vibration during bonding process. Bond pad contamination like silicon dust on bond pad or even deep probe mark and bond pad corrosion is a possibility. Smash ball is another defect, which is simply an overbond. If all bonds have the same manifestation, in most cases this is due to bond parameters are too high. Another possibility could be the bond height is not learned properly. In this case, you will see a smash ball or overbond on random wires. Die tilt caused by improper die-attach process can also lead to the same problem. Indication of this is the problem is only happening on some devices and it is localized within the device. Golf club ball is a defect where the bonded ball actually looks like a golf club. This happens if free air ball is not sitting properly on the capillary tip prior to first bond cycle. It could be due to wire tension setup or a kink tail when prayer ball was formed, or balls too big. Bond crater is a defect where part of aluminum bond pad or metallization came up with the mash ball, exposing and damaging the oxide layer underneath, which looks like a crater. This defect is typically associated to bond parameters too high or not optimized. Some devices are more prone to bond crater than others. In this case, it is quite important to optimize bond parameters to address the problem. Oversized ball is simply due to prayer ball is too big. Reducing the prayer ball size will correct the problem. Overbond stitch is due to bond parameters too high, particularly the bond pores. Reducing the bond pores will likely correct the problem. Optimizing capillary design may also help address the issue. Particularly larger base angle will improve shape of stitch and may allow higher bond parameters without overbonding. Tail on stitch is an indication that wire after second bond is not breaking properly. This can be due to second bond is too light as shown on the image, which can be due to improper second bond parameters. Also, different lead frame or substrate lead finish will result to different surface hardness and usually requires different second bond parameters. The last image on the bottom right is a weak second bond defect. Visually, it looks weak because of the small and thin fishtail. The weak bond can be confirmed through wire pull tests. Also notice that the capillary impression is light and incomplete. About half of the capillary impression is missing. An incomplete capillary impression is an indication that transducer is not mounted properly. This will also affect first bond quality. To address the stitch shape of a weak second bond, optimizing capillary design will certainly correct the problem. Testing bond strength is very important. Visually, the bond may look good, but this can only be confirmed after bond strength testing. There are two industry standard methods required to mechanically test bond strength. One is bond shear test and the other is wire pull test. Both tests are destructive. That's why the tests are done during machine setup prior production run. The machine or process is not released to production until the test is complete with the pass result. Depending on the number of wires, the test is done on all wires or just sample of wires. The bond shear test methodology is a documented JEDEC standard JESD 22-B116 titled Wire Bond Shear Test. This is a pre-standard that you can download from JEDEC website. Wire pull test methodology is documented in MIL Standard 883 Method 2011 titled Bond Strength Destructive Bond Pull Test. If you have any questions, you can drop a comment or send me an email. Please don't forget to like, subscribe, and share this video. Thank you for watching. Hey guys, welcome to another learning session from Watch, Learn, and Play channel. This time, I will talk about how to set up a wire bonding process, specifically ball bonding using gold wire. Gold wire bonding is one of the main interconnect processes in semiconductor packaging. It is widely used because it is a proven and stable interconnect process technology, and it is really a high throughput process that is very appropriate in a high volume manufacturing environment. I previously shared 3 learning videos related to wire bonding process that provided lots of technical information. And this information will now be applied in this next learning video. If you have not watched them yet, I strongly recommend to watch these videos as well. Okay guys, this is Lito Galera, and let's start learning. To set up a proper wire bonding process, you need to understand the device or die that you will be bonding. The key information that you need to know regarding the device are bond pad opening or BPO, bond pad pitch or BPP, bond pad composition, the required wire diameter, die size, die thickness, and bonding layout. Top left illustration on this slide shows about BPO and BPP. On the top right shows how BPO and BPP will affect the choice of capillary that should be used. On the bottom left shows how die thickness may affect loop height setup. A thicker die would leave less space to the top of the package, thus limiting the allowable loop height. With a thinner die, there is more room for a higher loop height. This slide shows variations in bonding layout. The illustration on the left shows a simple bonding layout wherein the bond pods are almost perfectly lined up opposite the leads. With this layout, the wire spans are generally shorter and do not require special looping parameters. The illustration on the right shows a bonding layout where some of the wires are on an angle away from the bond pod and also passing close to the edge of the adjacent bond pod and a longer wire span. Once you know your device, it is now time to select your bonding capillary. In general, there are two types of capillary based on how the capillary tip is shaped. First is the standard capillary, wherein the tip has a conical shape, typically with a main taper angle or MTA of 30 degrees. The second type is the bottleneck capillary. The tip is also a cone shape, but with a secondary shape that is slimmer than the standard tip shape. More illustrations on this slide using a bottleneck capillary. You see how capillary tip diameter should be relative to BPP. In general, capillary tip should be less than 2 times BPP to have enough gap to the adjacent wires. And also note the required bottleneck height or BNH relative to the loop height. Die size and thickness will affect wire span and loop height respectively. Wire span will affect selection of wire type. A long wire span would require stiffer wire than normal. And finally, wire diameter will determine the capillary hole diameter. This slide shows the capillary tip dimensions. Chamfer diameter or CD and chamfer angle or CA mainly affects the first bond. CD affects the mashable diameter or MBD. A small MBD requires a small CD, and a larger ball would require to use a larger CD. You will need to note that MBD must be less than the device BPO. CA affects the bonded ball shape. Typical chamfer angles are 70 degrees, 90 degrees, and 120 degrees. The illustration on the left compares the bonded ball shape between a 70 degree and a 120 degree CA. The second bond or stitch is mainly affected by face angle or FA, outside radius or OR, and tip diameter or T. Standard FA are 0 degree, 4 degrees, 8 degrees, and 11 degrees. FA affects the thickness of stitch. I would recommend to start with FA of 8 degrees, as it is not too thick and can compensate for higher second bond parameter if necessary. T dictates the stitch length, which is typically half of the T. OR dictates the profile of the stitch. It's time to talk about machine setup. In a production environment, the wire bond process is typically done using a semi-automatic or a fully automatic machine. The main difference between a semi-automatic and a fully automatic machine is the magazine handling system. A fully automatic machine has an input and output magazine handling system. The devices for bonding, typically in a strip or panel form, are placed inside the magazine and onto the input handling system, and then transported to the bond site where the actual bonding process happens, and out to the output handling system without operator intervention. A semi-automatic machine has no input and output handling system. The devices for bonding are placed manually onto the bonding site one at a time and also unloaded manually by the operator after the bonding process is complete. The bonding process happens at the center of the machine, which includes the heater block, the XY table, bond head, warped system, and the electronic flame up unit. These parts of the machine shall be discussed in this learning video as we go through the steps of setting up a wire bonding process. Before a bonding process can be set up, the machine itself must be first set up and calibrated. XY table controls the bond placement. With the bare small bond pad, the XY movement accuracy is critical. Otherwise, the bonded ball placement will be inconsistent or misplaced and partly overshoot outside of the bond pad area, which will cause bond shorting issues. The bond head, which carries the transducer and bonding capillary, controls the said movement during bonding, which means it controls the consistency of bonded ball thickness or flatness. Transducer frequency will depend on machine manufacturer and model, typically 60 or 120 kHz. Both the XY table and bond head must be calibrated or tuned before setting up the process. You should refer to the machine manual for proper procedures to do the calibration or tuning process. One of the key parameters in ball bonding is the bonding temperature. Heater block is key in ensuring correct bonding temperature throughout the bonding process. The heater block temperature is calibrated by measuring the actual temperature and compare it against the specs. The temperature measurement must be done with the window clamp and insert installed and in a closed position, using a calibrated thermometer. A deviation within a plus-minus 5 degrees C to the target temperature is typically acceptable. I would reiterate to use a calibrated thermometer for this activity. A higher temperature than the specs may cause damage to laminate substrate, particularly for BGA packages. Too much heat will also cause oxidation on copper-based lead frame. But of course, a higher temperature will increase material bondability. A lower temperature may not cause substrate damage or lead frame oxidation, but it makes bonding a little bit more difficult. It is now time to install the capillary. While capillary installation may look simple, it can create a lot of problems, if not done properly. The illustration shows a typical transducer and capillary. The capillary is installed or clamped at the end of the transducer using a clamp screw. However, the screw must be tightened at a certain torque and must be inspected or replaced after a certain number of times the capillary is changed. This is because the clamp screw affects the transducer tuning or calibration. A worn-out screw will result to higher transducer impedance and will likely affect application of ultrasonic power during bonding process. Make sure to follow bonding machine manufacturer instructions for installing capillary and transducer tuning or calibration. For proper bond placement, it is very important that the capillary tip and camera crosshair are, as much as possible, perfectly aligned. When you create a bond program, you use the crosshair to teach the bond placement. And when you do the actual bonding, the center of the capillary will land on the crosshair. So if the capillary is off-centered to the crosshair, then the bond placement will not be correct. Every time you change the capillary to camera offset should be taught. A quick illustration is shown on this slide. A capillary mark or impression is done on a bondable surface. Initially, the capillary mark will be off-centered to crosshair. After adjustment, the capillary should be aligned to the crosshair. It's time to talk about bonding trials. To do bonding trials, obviously, you need some materials to bond. Ideally, you would like to bond on actual die, but not the electrically good die. Only the ink dyes with good bondable bond pads. If ink dyes are not available, using just the lead frame or substrate is also acceptable. Using the available bonding material, you can now create the bond program. And also, just use a standard loop profile for simple and easier bonding trials. The main goal of the bonding trial is to make it stick. Make it stick. Well, needless to say, a successful bond means the first bond or gold balls stick onto the aluminum bond pad, and the second bond or stitch stick onto the lead. Likewise, you cannot do much if any of the bonds do not stick. For initial bonding trials, making the first and second bond stick is the first goal. And from there, you can play around with the parameters until you meet the bonding specs for both visual, bond shear, and pull tests. Let's now talk about how to make the bonds stick by understanding the fundamentals of bonding process. First bond is the bonding of free air ball to the bond pad. A bond pad is a small area of thin layer of aluminum. First bond requires a small amount of force to press the free air ball onto the bond pad, followed by ultrasonic power to form the bond between two materials. The bond is a very thin gold aluminum intermetallic layer, and the strength of the bond depends on the amount of intermetallic formed. The bond intermetallic is formed within the contact area between the bonded or mash ball and bond pad. The larger the mash ball, the larger the contact area, and the higher percentage of intermetallic formed. More intermetallic means higher bond strength, which is ideal in the bonding process. Let's examine the bonded ball after the first bond is complete. The bonded ball or mash ball diameter is typically should be in the range of 2 times to 4 times of wire diameter, or nominal 3 times wire diameter. For example, if you are using a 1 mil wire diameter, the target nominal diameter is 3 mils. Just to note, 1 mil is equivalent to 25 microns, therefore 3 mils is equivalent to 75 microns. On the mash ball diameter limit, it is possible that it is larger than bond pad opening, or BPO. It is critical that the mash ball diameter be within the BPO, otherwise there is a risk of bond shorting to adjacent pad or wire. On the low side of the limit, while 2 times wire diameter will very likely be inside the bond pad, it is likely will result to a lower bond strength because the contact area will be smaller. Because of the inherent shape of the bonded ball, the contact area is always smaller than the mash ball diameter. Also, the bonded ball height should be around 0.6 to 0.8 times of wire diameter. There is no universal bond parameter settings. Parameters need to be defined throughout bonding trials. While there are many bonding parameters, depending on equipment manufacturer, the primary parameters are bond force, ultrasonic power, and time. Learning how to play these parameters is very important and definitely will help you successfully set up your bonding process. The second bond is the bonding of the wire onto the lead, which completes the bonding sequence. Similar to first bond, bond force is applied to press the wire onto the lead and using ultrasonic power to form the bond. Because the second bond is on the lead, which is a much harder material compared to aluminum bond pad, it requires a much higher bond force and ultrasonic power to make the proper bond. The second bond strength is relative to the contact area of the wire to the lead, which is limited by the wire diameter, capillary tip size and shape, and bond force. Let's examine the details of a completed second bond. One side of capillary is pressed onto the wire by the application of bond force. This forms the fishtail of the second bond as shown on the image. The lead surface will also have the capillary tip impression, showing that sufficient bond force was applied during bonding. Notice how the shape and size of capillary affects the formation of second bond fishtail. Also note that second bond is also called stitch. If too much bond force is applied on the second bond, the stitch will be smaller and the capillary impression is deeper or shattered. In some cases, this will also result to a lifted stitch problem because the fishtail that is left on the lead is too small. Or if the stitch is not lifting, the tail end formation after second bond will be inconsistent and will cause a frequent or occasional EFO error when forming the pre-air ball. A poor second bond will also result to a low pull test results. Finally, let's talk about wire bond process quality requirements. These will apply only if you bond using actual dies. First, the visual quality. Bonded ball and stitch placement must be within the bond pads and leads consistently, and placement should not vary between devices. For first bond, make sure there's no golf clubbing, which means the wire must exit from the center of the bonded ball. Otherwise, it will look like a golf club. Next are the destructive tests, which are bond shear and pull tests. You can refer to JEDEC standard JESD 22-B116 for bond shear tests and MIL standard 83 method 2011 for bond pull tests. Lastly, you can do a bond crater test for first bond to check for oxide damage underneath the bond pad. That concludes our wire bond process setup learning video. Feel free to drop a comment or send me an email if you have questions related to this topic. To support my channel, please do not forget to subscribe, like, and share this channel. Thank you for watching. Wire bonding is the most popular interconnect process in semiconductor packaging, particularly for standard packages with single die. The basic wire bonding process connects a die aluminum bond pads to the silver-plated leads of a lead frame for leaded packages, or to the gold-coated bond pads of laminate substrate for BGA packages. For ball bonding using gold wire, the pre-air ball is always bonded onto the die aluminum bond pad, while the second bond or stitch is bonded directly to the surface of the lead frame or substrate. This bonding method is called forward bonding. Having the first bond on the aluminum bond pad prevents damage on the die, as the pre-air ball absorbs a bond force and prevents direct contact and impact of capillary tip onto the die. In this video, I will talk about two wire bonding techniques that are very useful in multi-chip, system and package, or hybrid packaging applications. Let's start learning. Standard IC packages such as SOP package family or QFN type packages have package thickness that gives enough space for a thick die and normal wire loop. IC packages that have body thickness of more than 1 mm have enough space for a normal wire loop. However, for applications that require a much thinner package, or let's say less than 1 mm thick, a thin die and low loop wire bonding is needed. For a less than 1 millimeter thin package, using a standard loop bonding is not possible, as the top of the wire will be exposed. Applying low loop bonding, the loop height can be under the top package, thus the wire is not exposed, but still the wire will be very close to the top package, which leaves a very small margin of error per loop height that can lead to a serious quality issue or product failure. A low loop normal bonding is used widely in both single chip and multi-chip packages. However, there is a limitation on how low the loop height can be achieved in low loop bonding without damaging or breaking the wire. Note that to form the wire loop, the wire must be bent in reverse and forward motions, and these bending motions mechanically stress the wire. The stress is actually concentrated on the bending line just above the bonded ball, or what is called the ball neck. As previously mentioned, very low loop height will likely cause damage on ball neck. To address the low loop height limitation, a special bonding technique called reverse bonding should be used. In reverse bonding, the first bond is placed on the lead or substrate, and the second bond is on the die bond pad. There are some advantages in using reverse bonding method. It allows a high kink height on top of the ball, which reduces bending stress at ball neck. Also, the bonded ball on the lead or substrate allows greater and better contact area that improves bonding strength that is particularly weaker with stitch bonded onto the lead or substrate. This is very important in SiP or hybrid packaging, where substrate pads are not the typical soft gold-coated surface. Here are some examples of reverse bonding in advanced packaging applications. Let's now look into the structure of reverse bonding, particularly on the top of the die where the second bond or stitch was bonded. We know that the stitch cannot be bonded directly on the die bond pad because of the capillary impact during second bond will damage the die surface. To do the reverse bonding properly, a bonded ball, or what's commonly called bump, is bonded on the bond pad and the stitch is bonded on top of the bump. This prevents damage on the die surface and secures bond between the bump and stitch. To do the process of reverse bonding described in previous slide, another special bonding process is necessary. The process is called BSOB, and for some, it is called SSB. BSOB is an acronym with many meanings, depending on the company or person you are talking to. It can be ball stitch on ball, bond stitch on ball, or even ball stitch on bump. SSB is also an acronym that stands for stand-up stitch bonding, or there could be other meaning to it. But regardless, BSOB is the same as SSB. Let's understand the BSOB process using this simple animation. Just like the normal gold ball wire bonding process, it starts with the pre-air ball hanging on capillary tip. The capillary then descends towards the lead to bond the bump. The first cycle is complete after bonding of the bump and forming of the new pre-air ball. The bonding then proceeds to the die bond pad and the formation of the wire loop and completing bond cycle with bonding of stitch on the bump. This process cycle is repeated until all wires are completed. BSOB is not only for reverse bonding. It is also useful for SiP or hybrid packaging where different substrate materials and bond pads are used, which makes second bond or stitch bonding very difficult. An example of this is the device shown on this slide. It is using a substrate with printed thick film material as bond pads. The thick film thickness is not as uniform as the typical pads of a BGA substrate, which makes bonding of stitch more difficult. The die While it is not a fine pitch device, the bond pad openings is small, which is the same as that of a fine pitch device. This means a smaller capillary tip must be used, and this increases the bonding difficulty of second bond. Using BSOB or SSB technique simply addresses the bonding issues for this kind of device. There are many other applications for BSOB or SSB and reverse bonding techniques. Knowing the basic concept and principles of these techniques will help you address many bonding issues that you may encounter in product development or on production floor. That concludes another learning video in semiconductor packaging. Feel free to drop a comment, question, or email. To support this channel, please don't forget to like, subscribe, and share this video. Thank you for watching. Hey guys, welcome back to my channel. Packaging of semiconductor devices involves many processes, from thinning of wafers and cutting to individual chips, to mounting of each die to a lead frame or substrate, and then the very critical interconnect process of wire bonding or flip chip technology. Once all these processes are done, the packaging is almost complete. But up to this point, the semiconductor device and all wires or interconnects are still exposed and prone to damage from mishandling and from the hazards of the environment. After the interconnect process, the device would need to be encapsulated. I will discuss in this video the two molding processes that are being used in semiconductor packaging industry. Okay guys, let's start learning. Semiconductor devices are very fragile and can be damaged in an instant if not encapsulated properly. There are several ways to encapsulate semiconductor devices after the interconnect process is complete. Transfer molding and compression molding are the two molding processes that I will talk about in this video. Transfer molding is widely used for lead frame based packages, such as plastic dual inline package, and also for small outline package types, such as SOIC, SSOP, TSSOP, and likewise for quad flat package, or QFP, and also the leadless QFN package. Transfer molding is not limited to lead frame based packages, as it is also widely used in BGA package, particularly wire bonded BGA. Compression molding is popular for advanced packaging, such as panel level package or PLP, and also for wafer level package or WLP. The complexity of these packaging technologies make them very sensitive to warpage and damage due to mold material flow. Transfer molding is a conventional method and one of the most common methods of encapsulating semiconductor devices, both for leaded packages and BGA packages. In transfer molding, the mold tool may have multiple cavities to mold several lead frame or substrate in a single mold shot to maximize productivity. The mold material is thermoset in pellet form. The number of pellets to use per mold shot is calculated based on the package size, number of units or package per shot, mold design, and mold press capacity. Transfer molding process in semiconductor packaging involves three main steps. First is the preheating of the molding compound. Second is the actual transfer molding process. And lastly, the curing of molded devices, which is called post-mold cure or PMC. Preheating is done using a high-frequency preheating machine that is made for thermoset molding materials. Preheating the molding compound improves material flow and shortens molding time. The preheating process is done while preparing for the next mold cycle to avoid wait time and improve productivity. The mold is split into top and bottom molds that form the top and bottom sides of the package. The mold contains the runner system, gates, and cavities. The mold also has a built-in transfer pot that connects to the runners. In the transfer molding process, the preheated epoxy molding compound or EMC pellets are placed into the transfer pot where it is heated to its melting temperature. Top and bottom molds are preheated at required mold temperature. The mold will close at certain clamping pressure to make sure that the runners and cavities are sealed to ensure proper mold flow and avoid mold flashes. The plunger pushes down the melted EMC at a certain level of transfer pressure to the runners and towards the mold gate to fill the individual cavities within the predetermined mold transfer time. Mold gates are critical to the molding process as it controls the flow of material to the cavity. It can get debris or material residue that may partially block the gate, causing incomplete molding. With that, the gates must be located so it can be accessed easily for cleaning. The gate should also be positioned to minimize wire sweeping, particularly for large packages that require long wire span. Air vent is also important to prevent trapped air while the molding compound flows and fills the cavity. Air vent is typically placed at the corner of the cavity that will fill last. It must be small enough to let the air escape, but not allow the molding compound to pass through. There are certain machine and process parameters that must be set and controlled for a proper molding process. First is the temperature. The mold temperature must be high enough for rapid curing of the part. Mold temperature must be controlled within a certain tolerance, otherwise process problems would be expected. For example, too high a temperature will lead to solidification of molding compound before completely filling the cavities, while low temperature will not be enough to cure the mold material. Generally, plus minus 5 degrees C tolerance is acceptable. Considering the size and number of cavities of the mold, multiple heater cartridges are installed in both the top and bottom molds to heat the cavities evenly. Mold clamping pressure, and transfer time are the other critical mold parameters. Clamping and transfer pressures ensure the flow of material to fill all the cavities. Clamping pressure ensures that the mold is fully closed during polymerization. Transfer pressure is applied by the plunger. Transfer pressure forces the mold compound through the runners and gates to the cavities. Transfer pressure controls the transfer time. The higher the pressure, the faster the material flow, thus the shorter transfer time. In high volume manufacturing, shorter cycle time means higher throughput, which means shorter transfer time is preferable. However, a higher transfer pressure is not always desirable. Mold material passes and pushes through the wire, and higher transfer pressure may lead to wire sweep and cause wire short within the package. During the transfer process, the molding compound goes through a reaction and changes its viscosity until it gels. Once gelled, the molding compound is already cross-linked. Once the cavities are filled, packing pressure is applied on the mold. Approximately after a couple of minutes, the molding compound is cured. Once cured, the mold will open and the mold devices will be ejected by the ejector pins. Typically, molding compound suppliers will have a recommended mold parameters for a specific material, which can be used as baseline parameters in setting up the mold process. Sumitomo is one of the leading suppliers for molding compounds. Example of their product line for semiconductor packaging is shown on this slide, and also an example of their technical datasheet for EME G600 compound. You will notice that at the bottom part of the datasheet shows the recommended mold parameters for the said compound, such as transfer pressure, mold temperature, cure parameters, and post-mold cure parameters. Advanced packages such as 2.5D and 3D have critical requirements that are not possible with transfer molding without risking catastrophic device failure. 2.5D and 3D packages require stacking or multi-stacking of thin silicon chips, fine pitch mini bumps per flip chip, or long span of fine wire diameter for bonding to be packed inside the thin package within a limited space. The limited space constrains the resin flow, while long wire span of small wire diameter is prone to wire sweep due to transfer pressure, and thin dies may crack with mold packing pressure. Towa Corporation of Japan is a molding technology company. They develop compression molding process technology with minimum compound flow. This is possible because in compression molding, there are no transfer pots and runners. The resin is put directly into the cavities where it is melted. The panels then dip face down to the melted resin for molding. Because the resin is put directly into the cavities, the compression molding process has minimum material flow. This is very important in avoiding wire sweep or damage on wire bonded devices that are using thinner wire diameter and long wire span. Also, the elimination of transfer pots and runners reduces the mold cycle time and significantly reduces mold material waste. With no mold gates and using release film, compression molding keeps the mold cleaning process to a minimum. That concludes another learning video in semiconductor packaging. Feel free to drop a comment, question, or email. To support this channel, please don't forget to like, subscribe, and share this video. Thank you for watching. Hey guys, welcome back to my channel. BGA package is a very popular package type in the semiconductor industry, particularly for advanced integrated circuits such as microcontroller, microprocessor, ASIC, memory chips, and graphic chips. A BGA package may contain a single high-pin count ICs or several ICs of different functions to form a complex system in package, and more recently a much more complex system that is popularly known as chiplet. Okay guys, let's start learning. BGA stands for ball grid array, which is the formation of the I/O terminals or solder balls on the bottom of the package. There are different variations of BGA packages according to its body size, solder ball pitch, package thickness, and solder ball configurations. There are also variations in the packaging interconnect process, which is a choice between wire bond and flip chip, and also on the processing complexity, such as multi-chip or stack die inside the BGA package. I will discuss details of BGA package variations along with assembly processes in this presentation. Plastic BGA or PBGA is one of the early versions of the BGA package. It is a molded package with a wire bonded device. JEDEC package code for PBGA is MS-034 with package size of 7 by 7 mm up to 55 by 55 mm. The package is a square shape. Package thickness is from 0.6 mm to 2.6 mm with solder ball pitch options of 1.27 mm and 1.5 mm. Some of the advantages of the PBGA package is high interconnect density and lower assembly costs. With wire bonding as the interconnect process, traditional IC bond pad layout is acceptable without the need for additional expensive RDL and bumping processes. Fine pitch bonding capability allows processing of higher pin count ICs. The substrate layers routing is also flexible and easier with the I/O solder pads arranged in an array underneath the package, which is not possible with the leaded QFP package. Here's a quick comparison in package size between the 304 leads quad flat package or QFP versus 304 solder balls BGA package. The 304 leads QFP package has a body size of 40 by 40 mm and a footprint of over 42 by 42 mm with the leads. In comparison, a BGA package with 304 solder balls is only just over 26 by 26 mm in body size and footprint of about 31 by 31 mm. That is about 46% reduction in board space.
Fine pitch BGA or FBGA is a package with solar ball pitch of 1 millimeter or smaller, up to 0.4 millimeter pitch. With fine pitch solder balls, the package can accommodate very high pin count ICs within a smaller package footprint. And with higher pin count density, the package is quite popular for multi-chip and stack die applications. The package type is fully molded and can be a square or rectangular in shape. Body sizes ranges up to 27 by 27 millimeter, and thin package profile of under 1 millimeter is also available. Let's now talk about flip chip BGA. Flip chip significantly increases the number of I/O terminals per unit area and improves package electrical performance, making it very popular for high pin count and high performance ICs. Flip chip BGA, particularly large package sizes, is ideal for workstation processors, high bandwidth system for communication devices, gaming system processors, and graphics, as well as high-end application processors for leading-edge portable devices. But flip chip advantage is not only about space. Advanced ICs and systems with thousands of IOs use a significant amount of power, and this power is transformed into heat, making the silicon chip so hot that it's more than enough to boil water. With flip chip technology, the die backside is exposed and available to directly attach a heatsink, and that it can also serve as a lid to protect the device. Obviously, heatsink diffuses heat from the device, thus improving the device's overall thermal performance. The variety of flip chip BGA package options allows package selection to be tailored to the specific thermal needs of the end product. High-end performance ICs typically uses lidded format that features a controlled thickness of thermal interface material that directly attach the die backside to a copper heat spreader or lead. This produces lowest thermal resistance between the package and any externally applied thermal solution or heat sink. Also, the lead effectively spreads heat laterally away from the die to the package perimeter and into the motherboard or PCB. Lower wattage products generally utilize bare die or molded package options. With flip chip technology, the solar bumps and core vias provides a lower thermal resistance path from the active side of the die through the substrate, allowing heat dissipation both from the die and package and into the motherboard or PCB. BGA package is about reducing board space and better performance, but this is not possible without having the right substrate material and design. So let's learn about BGA substrate, the industry standard, the materials, and the layers within the substrate. IPC 6010 series is a set of standards for printed boards, both flex and rigid, which includes laminate BGA substrate. I will discuss briefly some of these IPC standards in the next slides. IPC 6011 is the generic performance specification for printed boards. The scope includes general requirements for printed boards and the quality and reliability requirements. This standard also defines the different performance classes for printed boards. As defined in IPC 6011, there are three different classes for printed boards. Class 1 is the general electronics products, which includes consumer products and some computer and computer peripherals suitable for applications where cosmetic imperfections are not important, and major requirement is function of the completed printed board. Class 2 is the dedicated service electronic products, which includes communications equipment, sophisticated business machines, instruments where high performance and extended life is required, and for which uninterrupted service is desired but not critical. Certain cosmetic imperfections are allowed. Class 3 is the high reliability electronic products, which includes the equipment and products where continued performance or performance on demand is critical. Equipment downtime cannot be tolerated and must function when required, such as in life support items or flight control systems. Printed boards in this class are suitable for applications where high levels of assurance are required and service is essential. IPC 6012 covers the qualification and performance requirements for rigid printed boards, which includes most laminate substrate for BGA package. The standard covers different types of printed boards, from single and double-sided, with or without plated through hole, to multi-layer printed boards with plated through hole and with or without bias or micro bias. It also covers printed boards with embedded circuitries and metal core printed boards. Overall, the standard sets 6 different printed board types as shown on this slide. IPC has also defined sectional standards for rigid, flex, multi-chip module, and high-density interconnect printed boards. The standards provide applicable detailed requirements that are important and critical to design, fabrication, and qualification of printed boards. IPC 2226 for HDI contains details about construction and layers requirements applicable for BGA laminate substrate. The image represents the typical layers and construction of a laminate BGA substrate. The middle of the substrate is the core material with copper foil as conductor on both sides. On both sides of the core are built-up layers of prepreg and copper foil or conductive materials that are used for routing signals. Plated through-hole vias are formed to make the connections from top to bottom of the substrate. Buried and blind vias are formed to make connections between prepreg layers. The substrate core provides mechanical strength and stability to the laminate substrate. Depending on chip or system complexity, more layers are necessary to properly route the signal traces. Additional microvias, blind, buried, and stuck are created within each layer of the substrate. The core adds additional thickness to the substrate. In some applications, vertical space is limited, which means thinner package is required. To achieve a thinner package, the use of a coreless substrate is necessary. A coreless substrate makes connection between layers shorter, thus electrical performance is better. It is, however, prone to warpage, which may affect the package reliability. Core and prepreg are both layers within the laminate substrate. But what is the difference or similarity between these layers? The prepreg material is made of fiber or glass weave impregnated with the resin. The resin is hardened but left uncured, while the core is made of layers of prepreg that are pressed, hardened, and heat cured, and finally plated with copper foil on both sides. The heat curing process bonds the layers of prepreg, and the hardened resin cures through cross-linking, which set the core material properties. Let's now discuss the assembly process flow for a BGA package. BGA has many different configurations depending on package size, bump or ball pitch, package thickness, and interconnect process. But assembly process flow is mainly dictated by the type of interconnect process. There are 2 interconnect processes available for BGA package: wire bond or flip chip, or both. On this slide, we will talk about the assembly process flow for a wire bonded BGA package. A wire bonded BGA uses a standard die wherein the die terminals or bond pods are arranged on the die perimeter. The bond pods are metallized with aluminum suitable for wire bonding process. The assembly process starts with thinning the wafer to the required thickness, which is commonly called as the wafer backgrind process. After backgrind process, the wafer goes to the solve process, which is to cut the wafer into individual chips or die. BGA devices are typically thin and large chip size and with narrow substrate. With this, the wafer is mounted on a UV tape that sufficiently holds the wafer in place during the solving process. The die attach process is the process of mounting the individual chips or die onto the laminate substrate using adhesive epoxy or tape. The adhesive epoxy is typically heat cured to achieve the adhesion or mechanical strength required to hold the die in place for the next assembly steps and for the lifetime of the device. Once attached to the substrate and epoxy is cured, the device will proceed to the next step, which is the wire bonding process. The bonding process is a delicate process and requires the device, particularly the bond pad, to be very clean. The previous processes wherein the die is exposed to environment and also to the epoxy outgassing during curing process may introduce contamination to the bond pads, and likewise the leads on the substrate. The common process to clean the bond pads and the leads is the plasma cleaning process. Once plasma cleaned, the device is then ready for wire bonding process. BGA package is widely used for advanced ICs with many input-output pads. Advanced ICs are typically made smaller using new wafer fabrication technologies, and with hundreds of IOs, the bond pads are really small and pitch are tighter. In general, BGA package requires fine pitch bonding process using either gold or copper wire. In addition, smaller chip with a high pin count would result to a long wire span, and thinner package would require a low loop bond process. Overall, BGA wire bonding process requires fine pitch, low loop, and long wire span capabilities. After wire bonding process, the device is now more fragile with both the die and wires still exposed to environment and also prone to handling damage. So it is now time for molding process. Once molded, the wire bonded device will be protected and more rugged for handling. However, molding is not just about covering the chip and the die. It must stay intact, solid, and robustly attached to the surface of the die and the substrate. To achieve this, it is critical that the die and substrate surface are free of contamination. The exposure to heat and environment during wire bonding process can lead to some degree of contamination. Similarly, plasma cleaning the wire bond device will clean both the die and substrate surface. After a molding process, the next assembly steps are more straightforward. The BGA package is laser marked for required identification, which typically includes a device code, date code, and manufacturer location. Other information are added if needed and if space allows. Next steps are ball attach and singulation. After singulation, the individual package devices are electrically tested. Finally, I'll be discussing the assembly process steps for a flip chip BGA package. The first step is the bumping process, wherein the die bond pads are rerouted and redistributed to match layout appropriate for flip chip configuration. The bump wafer will then go through the backgrind process, where it is thinned to the required thickness, followed by the solve process to cut the wafer into individual bump chips. In some cases, bump dies are transferred to a carrier, such as tape-in reel or waffle pack, which can then be sold and processed in a smaller batch quantity. The steps to transfer bump dies into a carrier is called the pick and place process. After saw and pick and place process, the bump dies are now finally ready for flip chip process. The process is typically done using a high-speed flip chip bonder. Flip chip requires application of solder paste on substrate pads. There are many different types of solder that can be used for flip chip process, and some may or may not require additional flux to achieve good soldering quality. After flip chip, the populated substrate will pass through the reflow oven to complete the soldering process. After reflow, depending on the solder material used, the populated substrate may undergo a cleaning process in preparation for the next step, the underfill process. The underfill process uses epoxy resin, and it fills the gap between the bumps, die, and substrate. Once cured, the underfill provides solid mechanical support to both the die and bumps, preventing cracks on the solder joints and bridging the large gap in thermal expansion of silicon die and laminate substrate. Once underfilled, the package is ready for encapsulation, either by molding process or by using a metal lid that is attached to the die backside. Using metal lid gives better thermal dissipation, as the heat is transferred from the die to the metal lid and finally to an external heatsink. In some cases, there is no metal lid and the heatsink is directly attached to the die backside. The next process steps are ball mount and singulation. And finally, once singulated, the packaged device will go through 100% electrical testing. You can check my other learning videos for detailed topics related to specific processes, such as saw, wire bond, flip chip, and molding. That concludes another learning video in semiconductor packaging. Feel free to drop a comment, question, or email. To support this channel, please don't forget to like, subscribe, and share this video. Thank you for watching. Hey guys, welcome back to my channel. This presentation is about flip chip process and its importance in advanced packaging of semiconductor devices. The semiconductor industry is continuing to grow rapidly. The chip war between the US and China has triggered a significant change in the industry's landscape, currently shifting new and advanced wafer fabs to US and Europe to make more chips. And chips won't be useful unless they are packaged. So the advanced packaging industry is expanding as well. Okay guys, let's start learning. Flip chip is a popular interconnect process technology wherein the die is mounted face down onto the substrate. Using bumps instead of wires, flip chip allows the shortest possible connection between the die and substrate pads that will yield to better overall device electrical performance. With flip chip technology, smaller device and package footprint is possible with maximum number of I/Os. Most chips are designed for wire bonding process, which means the bond pads are positioned on the perimeter of the die, closer to the leads to allow a proper wire bonding process with the shortest wire possible. When the same chips are used for flip chip configuration, the original bond pads has to be redistributed. The new pads are redistributed as evenly as possible on the top side of the chip, forming a cluster or array of pads for bumping process. This is done through the addition of a redistribution layer or RDL. The RDL process involves adding 1 or 2 layers of metal and 2 or 3 layers of dielectric material, such as polyimide or BCV. The polyimide layer is added on top of the existing wafer passivation, and a layer of metal trace is added to reroute the bond pads. Another layer of polyimide is added to protect the metal trace, but also exposing the new pads for bumping process. The new redistributed pads have a different structure than a typical aluminum bond pad for wire bonding. This structure of new pads is called underbump metallization, or UBM. The new pads are for bumps that will provide the electrical connection between the die and the substrate. Flip chip reliability is anchored on the integrity of the solder joint between bump and UBM. A weak solder joint will ultimately result in device failure. The UBM structure has several layers and must be compatible with bumping technology. Typically, the first layer is on top and connected to the RDL metal. It is the adhesion layer and also acts as a barrier layer. The next layer is the wetting layer, and finally, the oxidation barrier layer. IBM developed the flip chip process in the 1960s. IBM bumping technology was popularly called C4, which stands for Controlled Collapse Chip Connection. C4 technology utilizes highlight solder bumps on pads of the chip and a matching wettable terminals on ceramic substrate. During the reflow process, the solder bumps will self-align to the substrate terminals. Unlike IBM high-lead solder and high-cost ceramic substrate, Sharp developed their own wafer bumping technology with thin lead solder and using standard FR4 substrate. The illustration on this slide shows the difference in UBM structures which were developed to match solder bump requirements. Integrated circuits have advanced significantly over the years, with silicon chips packed with more transistors for more advanced functionality, adding more I/O terminals while at the same time reducing the chip size. This means the bumps has to be much smaller and closer to fit the smaller chip area. Supporting the advancement in silicon chips are new bumping technologies, such as lead-free solder bump for standard pitch of up to 100 microns. Micro solder bump and copper pillar were also developed for much smaller fine pitch application. These bumping technologies are critical to development of advanced packaging that requires multi-chip solution in a single package. Flip chip on its own is very fragile mechanically. Also, the large thermal expansion mismatch between the silicon chip and PCB will lead to solder joint cracks, resulting to device failure. To improve flip chip reliability, the gaps between the chip and PCB are filled with epoxy resin. This is called as the underfill process. By filling the gaps, the thermal mismatch is reduced, while it also mechanically stabilizes the die and solder bumps. Underfill process is about dispensing the epoxy resin and have that resin flow underneath the die and between bumps to fill all the gaps between the die and the substrate. The epoxy resin will flow naturally between the gaps through capillary action, but only if the substrate surface is clean. However, in most cases, the substrate surface is not clean, particularly after solder reflow process. Typically, the area surrounding the solder bumps and around the die and passive components will have contamination due to flux residues. This contamination will prevent proper epoxy flow, resulting to non-wetting and voids, which will lead to device reliability issue. Most surface contamination on substrate are not visible by naked eye or even under microscope. You don't see it physically, but it is there on the surface. One way of checking is by contact angle measurement. A contaminated surface has low energy or it is hydrophobic. It doesn't allow the liquid to flow, which in the case of underfill process means the underfill epoxy will not flow properly between the solder bumps. A common method of cleaning the substrate surface in preparation for underfill process is plasma cleaning. Plasma cleaning uses gas such as oxygen and argon to remove organic contaminants. With the right gas mixture, it will remove organic contaminants and does not leave residue. It is also a green process, wherein gases used are non-toxic and has a harmless waste. After plasma cleaning process, the substrate surface has high energy and becomes hydrophilic, allowing underfill epoxy to flow properly around and between solder bumps. Ball grid array or BGA package is the most common package application of flip chip process. BGA package is best for integrated circuits with high number of I/O terminals. BGA terminals can be configured in many different ways, from several rows of peripheral I/O to full array configuration. BGA packages can use both wire bond and flip chip as interconnect processes. A wire bonded BGA is typically larger in size as the substrate wire bond pads are arranged outside of the die perimeter to accommodate the wire bonding process. With flip chip technology, the die is placed face down with die I/O bumps directly on top of substrate pads, thus eliminating the extra space needed when doing the wire bonding process. Using flip chip technology, the I/O density versus package area has increased significantly. Electrical performance of the package also improves with the shortest possible connection between the chip and substrate. The exposed die backside allows flexible thermal solutions, and the thermal interface material to have direct contact with the die surface, thus improving the package thermal performance. System in Package or SIP BGA package has a flip chip die and passive components mounted on the substrate. The flip chip die is underfilled and the die backside is exposed. This packaging option is generally for lower power applications, typically for less than 8 mm chip size. This is cost effective and has very good thermal performance, which is good for thermally demanding small device applications. This packaging option is called lidless BGA. Lidless BGA allows user to select the thermal interface material based on their requirements, and it is also applied after the solder reflow process. As mentioned earlier, lidless BGA is ideal for 8 mm or smaller chips for low power application. However, more advanced chips are larger, and larger die sizes exhibit greater package warpage due to the difference in thermal expansion between silicon and laminate materials. As a result, large die lidless BGA is more difficult to solder mount and may produce larger variations in bond line thickness between the die and external heatsink. To address the warpage issue, a stiffener ring around the periphery of the package substrate is added to provide structural rigidity. Another package option for flip chip technology is the leaded flip chip BGA package. It offers very good power and signal integrity and improved junction to board and junction to case thermal resistance as compared to wire bonded BGA package. The lid is generally constructed from a nickel-plated copper material. With the lidded flip chip package, the die is thermally coupled to the lid using thermal interface material. This material ensures good coverage as well as good thermal conductivity to further improve the junction to case thermal performance, and offers optimal thermal performance across a wide range of applications. It must also be able to withstand the high temperatures of solder reflow. However, while it is optimal, it might not perfectly meet customer requirements for high power or high ambient applications. Flip chip is also widely used in multi-chip applications. A classic example is a wire-bonded die on top of a flip chip in SiP package. In this option, a flip chip is mounted on an interposer substrate together with some passive components to form a sub-module package. The sub-module is then mounted on another substrate with other components. After solder reflow, another die is mounted face up on top of the flip chip device, this time for wire bonding process. Flip chip is also the interconnect technology to make a multi-chip module, or what's commonly called as chiplet, wherein several ICs are mounted on the same substrate to form a fully functional module or system. The substrate can be a multi-layer laminate substrate or a silicon interposer that is later mounted on another multi-layer substrate. That concludes another learning video in semiconductor packaging. Feel free to drop a comment, question, or email. To support this channel, please don't forget to like, subscribe, and share this video. Thank you for watching.